How do we determine the larger number without a calculator when we're given these two cube roots? I have the cube root of 200 and the cube root of 210. Now, most of you probably could figure out that the cube root of 210 is greater than the cube root of 200. And really the fact that 210 is a bigger number than 200 really, that pretty much is a good reason. But also kind of visualize this. What are we really talking about? The cube root is finding the edge length of a volume of 200. So we have a cube that has a volume of 200 and we have a bigger cube with a volume of 210. Well, that means that when we compare the edge length, the cube root is the edge length. When we compare the edge length of this cube with the edge length of this cube must have a longer edge length. This is a bigger cube. Okay, so we can say that cube root is edge length, and the number inside is volume. Therefore, bigger cubes have bigger edge lengths. Okay, so just geometrically we know that this is true. Okay, we can also just think of it in terms of numbers as well, and we can generalize that from the geometry. So example 5 says determine the larger number without a calculator, and when we compare these two roots. So this is a cube root of 200, the fifth root of 200. So this means I have a volume of 200 and I want the edge length. I don't really know what that number is, just like the same up here. But this is even more difficult because this is the same number, but it's a fifth root. And I don't really know how to visualize a fifth root, because once we get to cubes, we don't have shapes that are, in the fourth and fifth dimension. So how do we do this? Well, we can go back to repeated multiplication. In that we know that if we were to write this out, there's some number, x times x times x equals 200. And there's another number here that we'll call a times a times, maybe I'll just do this in color here so that we know which ones we're talking about. So here we have x times x times x equals 200. Okay, and over here we have some number a times a times a times a times a equals 200. Okay, now we know that x and a are numbers bigger than 1, so they are going to grow. They're going to get bigger as we multiply. And if we multiply by a 5 times and only get to 200, and we multiply by x 3 times and already we're at 200, we must be able to determine that the number x must be greater than the number a. And that means then we can determine that the cube root of 200 must be greater than the cube root of, let's say, the fifth root of 200. And this is a generalization we can make. We can say that the higher roots generally will give us smaller numbers. Now there is an exception in that if the actual number that we start with is less than 1, then that is the opposite relationship. Okay? We know that, and I'll give you an example over here. So if we multiply a number less than 1, we get a number less than 1. So let's say 0.9. So I know that the cube root of 0.9, and if I compare to the fifth root of 0.9, in this case, the opposite happens. We know that that's going to be bigger because we know that we multiply by some number 5 times and it was getting smaller every time, because every time we multiply by a number less than 1, it gets smaller. We only ended up getting to the size of 0.9. So we only shrunk it a little bit. Whereas here we multiply by a number less than 1, and we only did it 3 times, and we already got it to 0.9. So if we did it again, we get even smaller and even smaller. So this number here must be less than this number. And so the relationship here works when their number is bigger than 1 inside the root, but here is the opposite, because we would need a decimal number, and instead of growing, when we multiply by decimal numbers, instead of growing, we are shrinking the number. So the opposite relationship must hold true.